I decided to do a complete teardown in the Poundland GU10 LED lamp, and I wanted to reverse engineer this circuit board in it. So I'll just put this stuff out the way at the moment. To reverse engineer this, it's so small that I ended up taking a photo of it, then printing that out at quite a dark image, so I could see all the tracks and the components. Then I printed out a lighter image and drew the components on and how they were connected with lines. And then to finish that, I drew out the schematic. And I have to say there were a few surprise components on it. So let's look at the simplest bit first. The output of the circuit, this end of the circuit board, the transformer has 37 turns. It goes through one diode. There's a 22 microfarad 25 volt smoothing capacitor, then a 3K load resistor. I'm guessing that might be for discharge the capacitor quickly when you turn the lamp off. And then there's the 3 LEDs in series on this circuit board here. So I'd guess it's going to be, this is a 2.6 watt lamp, so it's going to be about 250 milliamps at the about 10 volts-ish across these LEDs. So I'm guessing that the 3K resistor, it could be possibly for a stabilization of the circuit, particularly if it goes open circuit, but also to make sure that when you turn the light off, it pulls the voltage on that capacitor down quite quickly, making sure they go off decisively without fading away for too long. So moving on to the rest of the circuitry now. The mains supply is connected here, and there's a single diode for the rectification, charging this slightly ungenerous 2.2 microfarad 400 volt capacitor. Then you've got the 203 turn primary of the transformer being switched by this small TO92 style package transistor here, which is a 13001, very common. And then there's also a 15 ohm sense resistor down here on the emitter of the transistor. And the purpose of the sense resistor is that as soon as enough current, if the current through this exceeds about 40 milliamps, the voltage across this 15 ohm resistor will rise to about 0.6 volts. And if it does, then it turns on this transistor here, and that will then shunt the base of the main transistor to the 0 volt rail, and it will basically turn it off. So that's probably just limiting the amount of current on each cycle. When you turn the unit on, the lamp on, initially current trickles through this 1 megohm resistor, and it just basically starts turning this transistor on. But as soon as it does start turning on, and current starts flowing through the primary, it'll induce current in this feedback winding, which is 10 turns. And this is coupled to the base via a 270 ohm resistor and a 14 nanofarad capacitor. Not sure if that's just maybe a tolerance thing, that the 14 nanofarad, but that's exactly what it measured. I tried 2 different capacitance meters. It just seemed an odd value. This capacitor here also probably has the function that when you turn it on, if this capacitor wasn't here, the current would flow through this resistor, and then it would just flow straight through this resistor and the winding, so it wouldn't probably go above 0.6 volts, I don't think. I'm not 100% sure. It might not just turn this transistor on. But anyway, when the circuit is running, the alternating current on the being induced in the windings is coupled through this capacitor and limited by this resistor. And this then brings us to this odd arrangement here. There's a 3.9 volt zener diode, an ordinary diode, and then a 10 microfarad capacitor. And I initially thought my meters were reading that wrong. I ended up using 2 different meters to measure the capacitor, because this here is the smallest 10 microfarad capacitor I've ever seen. Yet it measures with 2 different meters as 10 microfarad. Very odd. But the way this, as far as I can see the way that this works, I don't know if it's to do with regulation or open circuit protection, because if the load gets taken off or something like that, because it looks as though this capacitor here gets charged negatively by when the transistor turns off and the field collapses in the coil, in the little transformer, the current flow would be such that this diode would actually sort of charge this capacitor negative with respect to the 0-volt rail. And I'm guessing that I'm not 100% sure. I'm guessing that that means that because this end of the zener diode is being lowered negative to that rail, that that then acts as some sort of threshold thing that if it won't necessarily let this transistor be driven if the voltage in this is actually getting too high. It's very odd. It's quite hard to get my head around that. I've been trying to work that out, what it actually does. I don't know if it is regulation or if it's just open circuit protection. But yeah, it's quite interesting. If you're familiar with this circuit, it'd be quite interesting to hear about it. If you could leave a comment down below. But yeah, the circuit is very simple. Keep in mind this is the one that also ran on 12 volts. If you connected 12 volts across the input, it actually made the LEDs glow, and it was coupling through the transformer to do that. So it's a very sensitive circuit. It's very, very neat actually. I quite like the fact it just uses just a scattering of discrete components without the fancy chips used in the other drivers.